and he's going to talk about the use of linguistic structure in ELLIS. Thanks a lot, Omri. Whenever you're ready, you can go.
Okay, so let me just check that everything works technically. Can you see my screen okay?
Yes.
Yeah, okay. Because it appears to be a bit shaky, but hopefully we'll manage. Okay, so thanks a lot for this invitation. I will talk about some ongoing work we're working on at the lab on the use of linguistic structure in neural machine translation. And in accordance with the theme of this workshop, I'll try to frame it in broader terms. So neural MT and cross-lingual transfer, of course, has been making rapid progress over the past few years, and we're not really sure what makes them tick and when do they work and when not. So that was our starting point. The question of how and when the properties of the source and target language and their divergence and convergence patterns allow for effective learning, right? So what's the relation between the properties of the languages and the ability of the model to perform effective learning, in this case, in the context of MT. There are some works that have attempted, of course, such analysis, but I think mostly they have relied on a characterization of the languages in question in terms of typological database parameters, which are generally not probabilistic. They're not based on corpus statistics. They're coarse-grained and incomplete. They can be very useful, but in essence, what I'm saying is that they use a different language from from our standard NLP tools, right? So for instance, if we're looking at the differences between the syntax of different languages, then the parsers that we use, for instance, universal dependencies structures, they have different type of generalizations than when applied to a corpus than the ones you will find in typological databases. And I'll be more concrete. So basically, our program consists of 3 stages. The first one, characterization. We want to use, in our case, a parser. We use the universal dependencies parser in order to characterize the differences between the source and the target language, and to find out where they diverge and where they use similar syntax, but also to do it in a probabilistic way. So we'll get a distribution over what type of constructions in one language correspond to constructions in the other language. Using this characterization, we can now go and evaluate our systems and try to see what divergences impact performance and how. This will not only allow us fine-grained evaluation of system performance, knowing what type of constructions are easy or difficult to translate, but it will also be a fine-grained evaluation, which is termed again in the same language that we're used to in speaking about syntax in NLP. Again, universal dependencies in our case. Then building on gaps in performance that we'll be able to identify in step 2, we can then integrate the relevant linguistic structure to bridge any discovered gaps that we find. And I'll be more concrete now as to one implementation of this program using UD parser. So first, characterization. For that, we use the parallel universal dependencies corpus, which is a multiply parallel corpus with UD annotation, and we manually align the content words over 6 language pairs, so English versus French, Russian, Chinese, Korean, Japanese, and Arabic. And we basically our way to compare the syntactic relations between these 2 languages, or what constructions correspond to what constructions, was through dependency paths. So basically, we examine what is the joint distribution of dependency paths on one language and corresponding dependency paths in the other language. So in this example here, you can see a divergence between English and Korean, where a nominal modifier in English corresponds to a relation of a nominal modifier corresponds to a path of relative clause and then a nominal subject in Korean. So this type of analysis both reveals textbook divergences, such as the tendency to prodrop, which is different in different languages, of course, but also other cases which are more gradient tendencies of languages. For instance, adjectival clauses are the major correspondent of English non-possessive nominal modifiers in Korean. And this is something which just emerges from this corpus analysis. More importantly, for my purposes here, the induced mapping is data-driven, probabilistic, and uses NLP terminology and tools, which now we can take this language, right, the UD path language, and go and apply it to evaluation, right? So basically, we can now go and test our systems and try to see what divergences are difficult for them to bridge across. So which ones result in reduced performance and which ones do not. In this study, we looked at cases where a single source word translates into non-contiguous multiple target words, right? So for instance, in this example in German English, sich drängte, right? You need to translate them both. You need to understand that they're both form a lexical unit together in order to be able to translate it correctly into intruded. This is essentially what I mean by this type of divergence. How do we test system performance on these divergences? Well, here we took a pretty simple approach. We took a large test set. We used, again, the parser is able to identify sentences in which such divergences appear, essentially this type of divergences at least could occur. Then we can test the performance of the system on the entire test set and compare it to the performance of the system on the subset with this particular, on instances that contain this particular phenomenon. What we find is that this type of divergence results in reduced performance. So the performance on sentences with divergences is smaller than performance on the entire test set, and that performance deteriorates as a function of the distance between the non-contiguous parts. This, I think, relates also to the findings that to Jonathan's findings about generalization. In this case, perhaps not compositional generalization, but generalization over different positions. Okay, the third step of this program now acknowledges that if we have a language in which we can frame the differences between languages, and we can also identify cases of divergence in which performance is reduced, perhaps we can improve performance by allowing our system access to the type of structure that plays a role here. Or put differently, can we now go and integrate the UD information about the UD structures of the source and the target side into our MT system? And there's been several works, of course, that did that, but to the best of my knowledge, most of them in the context of transformers worked on the encoder side, on source side syntax. In this case, we looked at target side syntax, and basically we, in some sense, try to use the methods that we know work from source side syntax and see if we can apply them also to the decoder. Now, what did we do? Well, yeah, there are several methods we can use here for encoding graphs or trees, right? GCNs, or masking self-attention according to syntactic tree, or tree structured attention, and several others. But of course, when you do decoding, you don't know the structure in advance. You don't know the sentence in advance, so you need to parse and generate at the same time. And here we basically our approach starts from the statelessness of the transformer. So the fact that the transformer does not inherently rely on its past predictions. It's not really, it doesn't keep a hidden state of where it's at the prediction. It only, its only relation to its past predictions is that it auto-regresses on them, right? It kind of feeds them back in to the decoder, it re-encodes them. But if this is the case, well, then we can generate the output as a sequence of transitions. Say if we have a transition-based system for a transition system for the type of trees that we're interested in. For instance, in UD, of course, that's not a problem. And then when we generate the target side, what we do is we not only generate, we don't only re-encode back into the decoder the sequence of transitions that we've already produced, but also use it to compute the intermediate graph based on this sequence of transitions, and now use these established methods for taking the trees or the graphs, the intermediate graphs or trees, and re-encode them back into the decoder. Of course, there are many technical details here that I'm omitting for lack of time, but that's essentially the approach. The decoder and the encoder are, in some sense, very similar in the transformer, so this allows this type of reduction between decoding and encoding in a fairly simple way. Our results, so far we have results with automatic matrix only, but we see consistent improvement over the vanilla transformer where we use a UD decoder and a vanilla encoder as we do here. We have results on three target languages so far: German, English, and Russian. And we see that general improvement as well as improvement over the expected challenge sets, these type of divergences that I talked about before. Of course, in order to complete the loop, we will need to establish more firmly the relation between the properties of the source and target language, the information provided by the parser, and the performance improvement. But I think that if we take this kind of program, then they're all pretty much cast in the same language, that is the language of UD in this case. So to wrap up, we were looking at conditions that allow effective transfer and translation across languages. I believe there's a real opportunity here for the NLP community to develop a theory of differences and commonalities between languages that will also reflect or will help build a theory of evaluation of cross-lingual transfer and translation, allow relating the properties of the languages in question and the properties of models using a shared language. This can also feed back to model development, allowing the similar structures to be integrated back into our MT models, and of course, feed back to the ongoing discussion in the language sciences about the differences and commonalities between languages. I believe this program is applicable more broadly, but I think I'm out of time, so I'll just thank my collaborators, mostly Leshem and Dimitri, as well as my other collaborators, and thank you for your attention.
Right, thank you very much. Thank you very much for the talk. Are there any questions? Let me just wait a little bit to see if anyone types a question, or just feel free to jump in and ask. Okay, I have a question. So, the main idea of this model is to model syntactic divergence and to use syntax in the target side to improve the quality of MT, in particular for for languages that require that have very many differences in syntax. So if I understood correctly, in your model, your decoder generates a sequence of transitions that corresponds to parse tree or partial parse tree, and then you fed back this structure at each step to the decoder, right? What is the benefit, or I don't know if you looked at it, like is there a benefit between feeding the actual structure, which requires encoding the parse tree, versus just conditioning on the sequence of transitions using a regular autoregressive decoder?
Yeah, that's a good question. Yeah, so we also tried that where we only kind of linearize the target side graph as a sequence of transitions, and this seems to work. This seems to work less well. There's also a kind of a note which perhaps I should make. I didn't really have time for it, but is that there is a very important difference between the encoder and the decoder, at least in the transformer, and that is that the decoder kind of always masks, right? Each position masks the previous positions, right? Which means that if I, at some later point, encountered you know, a child or a parent of a node that I generated before, then just the standard transformer implementation won't let me, you know, won't allow me to kind of update the embedding of the parent that was generated before, which doesn't make a lot of sense in this case, where, you know, where we hope that the graph, you know, the generated tree or graph will somehow inform, you know, what should look at what, how the attention should work. So we also introduced this modification where you know, we don't have single-sided masking in the decoder, but rather it kind of recomputes the embedding of each position at each time based on whatever it has. And we also checked whether this gives an improvement. So it does, but it seems to be lower than the one you get from actually re-encoding. So yeah, so I'm not, that is not to say that I'm sure what's going on there. I mean, as I said, I think that in order to make this really convincing, we need to somehow show that, you know, specific cases where you really needed some syntactic information, like with the reflexive verb example that I saw, you really need to know that these two words work together and translate them together, and that we really translate on that specific case. So I think we're, you know, trying to narrow it down towards that angle, but we're not quite there yet.
Okay, thank you. Any more questions? Do you have any insight about you know, whether improvements in performance by using this decoder vary with the size of the data set? Like, I would expect you know, smaller data sets to be you know, to get bigger improvements because of these structural bias. Is that the case or not?
So I'm really hoping that it is, but our so far, that's another detail which I didn't have time to go into. So far, it seems that we need fairly high quality data and reasonably good parsers to apply over the, you know, over the data. So that's why we use the WMT data, which is pretty good. But in kind of other cases where we looked at, where we have our parsers are less good, or that our data is more noisy, for instance, Korean, we couldn't, at least so far, get a clean, and we were trying to clean it ourselves, but there seems to be, you know, some, that seems to be more difficult, at least for this type of architecture that I presented. And so, you know, low resource languages, they also tend to have less quality resources. So I don't know. That's a short answer, but I hope you're right. I mean, that's my intuition as well.
Okay, thank you very much. So now we are going to have a poster session.